A team of astronomers led by researchers at the University of Warwick has reported the discovery of a planetary system that does not follow the usual pattern seen in our own solar system. The discovery was made using data from the European Space Agency mission called CHEOPS, characterizing exoplanet satellite. The results were published in the scientific journal Science. The system orbits a small red dwarf star known as LHS 1903. To understand why this discovery is important, it helps to review how planetary systems are generally expected to form. In our solar system, the four inner planets, Mercury, Venus, Earth, and Mars, are rocky. They're relatively small and made mostly of metal and silicate rock. Farther from the Sun are the gas giants Jupiter and Saturn, followed by the ice giants Uranus and Neptune. These outer planets are much larger and contain thick atmospheres made mostly of hydrogen and helium, along with various ices. This general arrangement reflects how planets are thought to form inside protoplanetary disks.
If you enjoy deep dive science documentaries like this, focused on real data, real mysteries, and the edges of human knowledge, consider subscribing. New videos explore the universe where certainty ends and discovery begins. And let us know in the comments what you think. Thanks for watching.
Planetary systems begin with a young star surrounded by a rotating disk of gas and dust, known as a protoplanetary disk. Close to the star, temperatures are high. Light gases are heated and either blown away or prevented from condensing. Only heavier elements and minerals can remain, forming solid rocky bodies. Farther out, where temperatures are lower, gases can cool and accumulate. Planetary cores in these cooler regions can grow large enough to attract and retain thick atmospheres, eventually becoming gas giants. For decades, this framework has shaped how astronomers interpret new planetary systems. LHS 1903 is a red dwarf star, specifically an M dwarf. Red dwarfs are smaller, cooler, and dimmer than our Sun, and they are the most common type of star in our galaxy. Although they are faint, many red dwarfs are known to host planetary systems, and a large number of discovered exoplanets orbit stars like these. Astronomers using ground-based telescopes and space missions had already identified 3 planets orbiting LHS 1903. The innermost planet was classified as rocky. The second and third planets appeared to be gas worlds, much larger and likely surrounded by thick atmospheres. At that stage, the system appeared fairly typical, a rocky planet close to the star with gas planets farther out. However, when researchers studied the system more closely using CHEOPS, they found evidence of a fourth planet orbiting even farther from the star. This planet turned out to be small and dense. Measurements of its size and mass indicated that it is rocky rather than gaseous. This means the system follows an unusual pattern: rocky, gas, gas, rocky. Its presence in the outer region challenges long-standing assumptions about where solid worlds can form. The research team, led by Dr. Thomas Wilson at the University of Warwick, explored several possible explanations. One idea was planetary migration. In many systems, planets can move inward or outward over time due to gravitational interactions with the disk or with other planets. It is possible that the rocky planet formed closer to the star and later moved outward. Another possibility was that the planet originally formed as a gas planet but later lost its atmosphere. Large collisions can sometimes strip away a planet's gaseous envelope, and strong radiation from the star can erode an atmosphere over time, especially for smaller planets. After analyzing the data, the team found that these explanations did not match the observations well. The planet's orbit and physical properties did not strongly support simple migration or major atmospheric loss. Instead, the researchers proposed an alternative explanation known as inside-out planet formation. Inside-out planet formation suggests that planets form sequentially rather than all at once. In this model, planets begin forming close to the star and then form progressively farther out over time. The innermost planet forms first and gathers material from the disk. As it grows, it clears out nearby gas and dust. The next planet then forms farther out using the remaining material, and the process continues outward. In that case, the outer planet may have formed too late to capture a thick atmosphere. This suggests that the outer rocky planet formed in a gas-depleted environment. This is important because most traditional models assume that outer regions of disks remain gas-rich long enough to form gas giants. The presence of a rocky planet there indicates that timing can be just as important as location. CHEOPS played a critical role in this discovery. The mission is designed to precisely measure known exoplanets rather than to discover new ones. It focuses on accurately determining planetary sizes by observing transits, which occur when a planet passes in front of its star from our perspective. During a transit, the planet blocks a small amount of the star's light. By measuring this dip in brightness, scientists can calculate the planet's radius. When combined with mass measurements from techniques such as radial velocity observations, researchers can estimate a planet's density and determine whether it is rocky or gaseous. For the fourth planet, orbiting LHS 1903, CHEOPS provided more precise size measurements. These showed that the planet is much smaller than the gas planets in the system and has a density consistent with a rocky composition. Without CHEOPS's precision, this unusual structure might not have been clearly identified. This discovery has broader implications for planet formation theories. For many years, these theories were strongly based on our solar system, which was the only known example. Now, with thousands of exoplanets discovered, astronomers are seeing a wide range of planetary system layouts. Some systems contain gas giants extremely close to their stars, while others feature compact groups of super-Earths. Systems like LHS 1903 show that even the common rocky inside, gas outside pattern is not universal. This finding does not mean the standard model is incorrect. Instead, it suggests that planet formation is more flexible and complex than once believed. Different disk conditions, formation timescales, star types, and planetary interactions can all lead to different outcomes. Red dwarf stars like LHS 1903 are particularly important to study because of their abundance in the galaxy. Their protoplanetary disks may differ from those around Sun-like stars in mass, temperature, and gas retention. These differences can influence how planets form and evolve. The outer rocky planet in this system could be a rare case or part of a broader pattern that has not yet been fully recognized. Continued observations with CHEOPS and future missions will help determine how common inside-out planet formation might be. In summary, the planetary system around LHS 1903 challenges the simple expectation that rocky planets always form close to stars and gas giants form farther out. In this system, the sequence is rocky, gas, gas, rocky. Observations suggest that the outer rocky planet likely formed later after much of the disk's gas had already been used. This supports a sequential inside-out formation process rather than simultaneous planet formation across the entire disk. This discovery highlights how ongoing exoplanet research continues to refine our understanding of planetary systems. Each new system provides valuable data that helps improve existing models. Rather than overturning current theories, findings like this expand them and show that planetary formation can produce a wide variety of outcomes across the galaxy. If you enjoy clear explanations of space discoveries, consider subscribing to the channel.